Welcome back to Talk Tensors, everyone. Today we're going to be looking at mobile agents.
Oh.
You know, those little AI helpers, they're supposed to like automate stuff on our smartphones.
Yeah.
The thing is, training these agents has always been a bit of a headache. It usually involves like sucking up tons of user data to some central server.
Yeah, I see where you're going with this.
And well, that raises all sorts of red flags like cost, scalability, and of course the big one, privacy.
You hit the nail on the head. I mean, just think about it, right? The sheer amount of data our phones generate every single day is mind-blowing. And it's not just like random bits and bytes. This is sensitive stuff, personal stuff. So centralizing all of that in one place, it's a recipe for disaster, not to mention a massive privacy nightmare waiting to happen.
Right, exactly. And that's where I think federated learning comes in, right? It kind of flips the script on this whole data collection game.
It does. It's a real game changer. See, with federated learning, we're not sending all our data to some, big brother server. The training happens locally on each user's device. So your data stays on your phone, nice and secure, but the AI model still gets to learn from the collective wisdom of, potentially millions of users.
Yeah, it's like having your cake and eating it too, right? Privacy and power. That's the beauty of this distributed approach. Now, this brings us to the paper we're diving into today. It's all about tackling a pretty fundamental problem in this whole federated mobile agent space.
Yeah, so the researchers behind this paper, they really hit on something crucial. They noticed that there was a gaping hole in the research. There were no standardized benchmarks for training mobile agents using this federated learning approach. And without a common yardstick, a way to measure progress, it's like trying to run a race without a finish line. You can't really tell who's winning, or even if you're moving in the right direction.
Right. It's like, how do you compare different approaches? How do you know if you're making actual headway? So what did they do to fix this?
Well, they went ahead and created something called FedMABench. They call it the first benchmark specifically designed to train and evaluate mobile agents in this federated setting. And here's the kicker. They built it with a huge emphasis on what we call heterogeneous scenarios.
Heterogeneous scenarios. So not just assuming everyone uses their phone the same way, which we obviously don't.
Exactly. And that's what makes this benchmark so powerful. It acknowledges the real-world messiness of user data. We all have our own quirks, our own app preferences, our own ways of interacting with our devices, and FedMABench embraces that.
Okay, so FedMABench, a brand new testing ground for federated mobile agents, built to handle the Wild West of real-world user data. Sounds exciting. So break it down for us. What are the core ingredients that make up this benchmark?
So FedMABench is this really comprehensive toolbox. It's got 6 separate series of data sets, and they're further split into over 30 subsets, each designed to test a different aspect of this whole heterogeneity thing. And on top of that, you've got 8 different federated learning algorithms baked right in. So researchers can compare and contrast, see which methods work best in which situations. And then you've also got support for over 10 different base models. These are the underlying AI architectures that actually power the mobile agents.
Wait, so they're giving you the data, the algorithms, and the AI models. That's pretty generous.
It is, and it's all open source, too. You can find it on GitHub and Hugging Face. The researchers really wanted to make this accessible to the whole community to push the field forward.
That's awesome. So it's not just some theoretical paper. People can actually download this thing and play with it.
Right.
What kind of insights did the researchers get from their own experiments with FedMABench?
Oh, there were some really juicy findings. One of the most consistent things they saw across all their experiments was that federated learning consistently beat out training agents on individual isolated data sets, like hands down, every single time.
So even with all the differences in how we use our phones, the collective knowledge of the crowd wins out.
It does. It really underscores the power of this collaborative approach. But here's the catch. They also found that heterogeneity, all those variations in user behavior, it does have a negative impact on the overall performance. It's not a free lunch. There are challenges.
So it's like, yes, collaboration is good, but the devil is in the details, right? How do we handle those differences effectively? And you mentioned something interesting earlier, the distribution of specific apps mattering more than just broad app categories. Can you unpack that a bit?
Yeah, so it's not just about, do you use a shopping app? It's about which specific shopping app do you use and how you use it. Because those granular details, they really influence the training process. The researchers saw this when they compared the results from the category level and the app level data sets. Even when users were using apps from similar categories, if their specific app choices were different, the performance took a hit.
That makes a ton of sense. Two people might both be using shopping apps, but their experience on Amazon is going to be wildly different from their experience on, say, eBay. So capturing those nuances is super important. Okay, let's back up a bit and really dig into what makes FedMABench such a big deal. You mentioned it being the first of its kind. Why is that so crucial for this whole field of federated mobile agents?
Well, think of it like this. Before FedMABench, everyone was kind of playing their own game. Researchers were using different data sets, different metrics, different training methods. It was a free-for-all, and it made it almost impossible to compare results or track progress in a meaningful way. So FedMABench comes along and it's like, boom, here's a standardized playing field. Here are the rules. Let's get serious. And that's huge for a field that's still relatively young and evolving rapidly.
It's like going from a bunch of local tournaments to the Olympics. Suddenly everyone's on the same page. You can really see who's pushing the boundaries.
Exactly. And the beauty of it is everyone can access this playing field. It's not some exclusive club. The framework and the data sets are all available online on GitHub and Hugging Face. So anyone can download it, run their own experiments, compare the results to others, and contribute to the collective knowledge. It's a beautiful thing.
It's open science in action, which is always a win. Now, you also emphasize the focus on heterogeneous scenarios in FedMABench. Why is this so critical, especially when we're talking about applying this research to the real world?
Well, let's face it, the real world is messy. People are messy. Our data is messy. And if you want to build AI systems that actually work in that messy reality, you can't just pretend everyone is the same. You have to embrace the diversity. And that's what FedMABench does so brilliantly. It forces you to confront those differences in user behavior head on.
It's like you can train your mobile agent in a perfectly controlled lab setting, but the second you release it into the wild, it's going to encounter all sorts of things it's never seen before. So better to train it for that reality from the get-go.
Spot on. And that's why this emphasis on heterogeneity is so refreshing. It's a dose of realism in a field that can sometimes get a little too caught up in the theoretical.
Okay, let's get into the nitty-gritty. You mentioned data sets, framework algorithms. Let's start with the data sets. What kind of data are we talking about here? And what makes them so special?
So as I mentioned, there are 6 main series of data sets, and they're all carefully designed to poke and prod at different aspects of heterogeneity. Now, they actually start with 2 homogeneous data sets, basic AC and basic 8W. These are kind of like the control group, the baseline. They help validate the basic principles of federated learning before throwing all the complexity of the real world at it.
Got it. So making sure the foundation is solid before building the skyscraper.
Exactly. Now, basic AC, it has several subsets with different amounts of data, but all drawn from the same basic distribution, so you can see how the volume of data affects things. Basic AW, on the other hand, it comes from a completely different data source, just to add a bit of initial diversity. But the real fun begins with the 4 heterogeneous data set series. These are where things get really interesting.
All right, let's dive into the heterogeneous ones. These are the ones that are supposed to mimic real-world user behavior, right?
You got it. Each one tackles a different flavor of heterogeneity. First up, you've got the step episode dataset. This one's all about what they call 2-level heterogeneity. Think about it. When you interact with an app, you're performing a series of individual steps within a larger task, which they call an episode. So users can differ in both the number of episodes they do and the number of steps per episode. Some people might be power users, blasting through tons of tasks. Others might be more casual, taking their time.
It's like some people sprint, some people stroll, both valid but very different.
Exactly. And the step episode dataset captures that. It's got 4 subsets: IID, which is like the perfectly balanced scenario; episode skew, where the number of episodes varies wildly; step skew, where the steps per episode are all over the place; and both skew, where, well, both things are skewed. They even have these cool visualizations in the paper to show you what these distributions look like.
Okay, so that's heterogeneity in terms of how much and how intensely people use their phones. What's next?
Next up is the category level dataset. This one's all about the different types of apps people use. They grouped apps into 5 broad categories: shopping, traveling, office, lives, and entertainment. And then they created 6 subsets with different variations in how these category distributions are spread across users. So for example, one subset might have users who are super focused on just one category, like all they do is shop online. Another subset might have users who dabble in all the categories, but with different proportions.
So some people are specialists, some are generalists. Again, different strokes for different folks.
Precisely. And they have 52 different apps in this data set with 1,000 episodes sampled for each subset. It's quite a comprehensive view of app category usage.
Okay, so we've got how much people use their phones, what types of apps they use, What about like specific preferences within those categories? Because, two people might both use shopping apps, but one lives on Amazon while the other swears by eBay.
That's exactly what the app-level dataset is designed to explore. It zooms in on those granular app preferences. They picked 5 super popular apps: Amazon, Clock, eBay, Flipkart, and Gmail. And then they created 4 subsets that mirror the distribution patterns from the category-level dataset, but at the individual app level. So you can see how the popularity of specific apps influences the training process.
It's like, okay, we get it. You're a shopping app person. But are you an Amazon person or an eBay person? Because those are 2 very different beasts.
Exactly. And they sampled 150 episodes per app for this one. It's all about those fine-grained details.
Okay, last but not least, what's the final heterogeneous dataset series all about?
The grand finale is the Scale app dataset. Think of it as the app-level dataset on steroids. It's bigger, bolder, and designed to really push the limits of heterogeneity. They've got 30 simulated clients, 30 different apps, and a whopping 2,500 episodes. They even have this nice visualization in the paper showing the top 15 most frequently used apps in this dataset. It's a real beast.
So they threw everything but the kitchen sink at this one, really trying to capture the full scope of real-world app usage.
They did, and they still stuck to the IID, skew, and random distribution patterns so you can compare the results across the different data sets. It's all about consistency.
Okay, so we've got a pretty good handle on the different ways they've sliced and diced this user data. But what about the structure of the data itself? Like, what does a single data point that the mobile agent learns from actually look like?
So each data point is like a little snapshot of a user interaction. They call it an episode, and it's broken down into steps. Each step contains a high-level instruction describing what the user wants to do, a low-level instruction specifying the action to take on the screen, a screenshot of the screen itself, and the actual action the user took. So it's this rich, multimodal data point that captures the user's intent, the visual context, and the actual behavior.
It's like they're giving the AI a front row seat to the user's thought process and then saying, okay, now learn from this.
Pretty much. And for some of the data, they actually had to develop a clever dual strategy to extract the app names because it wasn't always explicitly available. They combined information from the user's actions and the high-level instructions. It was a bit of a data detective work.
Sounds like they went the extra mile to make this data as useful as possible. Okay, we've covered the data sets. Let's move on to the framework they built around this data. What's the big picture here?
So the framework, it's basically a classic federated learning setup. You've got a central server that holds the global model, and then you've got a bunch of clients, which are like our smartphones. The server sends a copy of the model to each client. The clients train it locally using their own private data, and then they send the updated models back to the server. The server combines all these updates into a new, improved global model, and then the whole cycle repeats.
The circle of federated life.
Exactly. It's a well-established protocol, and it works beautifully for this kind of distributed learning.
Okay, what about the specific algorithms they used for this federated learning? Because, there are different ways to skin this cat.
Oh, for sure. They didn't want to limit things, so they included 8 different federated learning algorithms in the benchmark. You've got your classics like FedAvg and FedProx, which are like the bread and butter of federated learning. But then they also threw in some more sophisticated algorithms like Scaffold, FedAvGM, FedAtom, FedYogi, FedAtagrad, and even FedMobileAgent, which was a previous research effort specifically focused on mobile agents. So you've got a good mix of the old and the new, the simple and the complex.
It's like a buffet of federated learning algorithms. Take your pick.
Exactly. And the beauty of it is you can directly compare how they all perform on the same data sets with the same metrics. It's a really level playing field.
Okay, now for the brains of the operation, the base models, what kind of AI architectures are we talking about here?
So they went with a pretty diverse selection here, too. They support over 10 different base models from several different families, including Qwen, Intern, DeepSeek, and even some OpenAI models. They specifically mentioned Qwen 2 VL7 edge AI models.
So you can basically plug and play with different AI brains and see how they perform in this federated setting.
Precisely. And they made sure to include both vision language models, which are great for understanding what's happening on the screen, and more traditional language models, which are more focused on processing text. It's all about finding the right tool for the job.
So you've got your data sets, your framework, your algorithms, your models. What about the actual process of training and evaluating these mobile agents? How does that all work within FedMABench?
So they have 2 main training configurations, high level and low level. The main difference is that in low-level training, the agent gets a bit more hand-holding. It gets told what its specific goal is on each screen, like a little mini instruction. This can sometimes help it learn faster. And then for evaluation, they use two main metrics: step-level accuracy and episode-level accuracy. Step level is all about how accurate the agent is on each individual action. Episode level is about whether it can successfully complete the whole task.
So like step level is about hitting all the notes, while episode level is about playing the whole song flawlessly.
Perfect analogy. And the framework itself, it's actually built on top of an existing open source repository called mSwift. So they didn't have to reinvent the wheel, which is always a plus.
Smart move.
Yeah.
Okay, let's get back to those key experimental insights you mentioned earlier. What were some of the biggest takeaways from all those experiments they ran?
Well, one of the most consistent findings, and this is really encouraging, is that federated learning consistently outperformed local training. Like across the board, it just worked better.
So the collaborative approach really does pay off. That's good news for the future of privacy-preserving AI.
It is. But, as with everything, there's a but. They also found that heterogeneity, that variability in user data, it does pose a challenge. The more heterogeneous the data, the harder it was to get good performance.
So it's like, yes, collaboration is powerful, but we need to figure out how to handle those differences effectively. And you mentioned earlier that the distribution of specific apps seemed to matter more than just broad categories. Why is that?
Yeah, so when they compared the results from the category level and the app level data sets, they noticed something interesting. Even if the distribution of app categories was fairly similar across users, if their specific app preferences were different, the performance took a hit. It suggests that those fine-grained details, like whether you're an Amazon person or an eBay person, they really matter.
So it's not enough to just know that someone uses a shopping app. You need to know which shopping app, because those interactions are going to be unique.
Exactly. And that's a really valuable insight for anyone building federated mobile agents. You can't just ignore those individual preferences. They matter.
Were there any particular federated learning algorithms that seemed to handle heterogeneity better than others?
Yeah, actually. They found that FedMABench, which was specifically designed for mobile agents, did a particularly good job on the step episode datasets. It seems to be better at dealing with the varying lengths of user interactions. There was also this interesting case where a local model, trained on data from just one client, actually performed surprisingly well on a specific subset of the step episode dataset. The researchers think this is because that client happened to have a lot of data that followed that specific skewed distribution.
So sometimes having a lot of even narrowly focused data can be an advantage.
Yeah, it's a good reminder that there's no one-size-fits-all solution in this space. It really depends on the specifics of your data and your task.
What about the other algorithms? Did they all react to heterogeneity the same way?
Not at all. Some were more sensitive than others. For example, FedYogi, which is this adaptive optimization algorithm, it really struggled on the category half-skewed dataset, even though it did well in other scenarios. It highlights the fact that the choice of algorithm really matters, and what works best in one situation might not work best in another.
So it's all about picking the right tool for the right job. What about the results from the Scale app data set, the one with all the clients and all the apps? Did those findings generally support the earlier ones?
Yeah, they pretty much reinforced what they'd seen before. The impact of app distribution was still very significant, and apps with fewer training examples, those so-called long-tailed apps, they really suffered in the heterogeneous settings. They also noticed this weird correlation between Amazon and Flipkart for one specific client, even though that client only had data for one of those apps. It suggests there might be some underlying similarities in how people use those two platforms, even though they're different companies.
Interesting. So even across different apps, there can be these unexpected connections in user behavior. The researchers also did some ablation studies, right? Looking at things like data set size, number of clients, participation rates. What did they learn from those?
Yeah, those ablation studies were really insightful. They found that, generally speaking, more data and more clients led to better performance, which isn't surprising, but it's good to have that confirmation. However, they also found that there were diminishing returns. Like, at some point, adding more data didn't really move the needle much. And they also found that you don't necessarily need all the clients to participate in every round of training. Having a decent percentage participate can get you pretty close to the same performance, which is good news for real-world deployments where devices might be offline or have limited bandwidth. Lastly, when they compared different base models, they generally found that bigger, more capable models performed better. But they also highlighted the potential of smaller models, especially if they're trained well using federated learning. Because at the end of the day, you want a model that can actually run efficiently on a mobile device.
It's all about finding that sweet spot between power and efficiency. Okay, now for the fun part. Novel notions. Time to put on our speculative hats and think about where this research could lead. What kind of crazy ideas are bubbling up?
Well, one idea that I think is really intriguing is this concept of personalized federated learning. Remember how the app-level dataset showed us that specific app preferences really matter? Well, what if we took that to the next level and actually tried to build models that are tailored to each individual user's app usage patterns? Like, instead of one global model for everyone, we have a bunch of personalized models, each fine-tuned to a specific user's needs.
So, like, my mobile agent is trained on my specific Amazon shopping habits, while yours is trained on your eBay obsession.
Exactly. It would be like having a personal AI assistant that really understands your quirks and preferences. And the beauty of federated learning is that you could still benefit from the collective knowledge of the crowd, even with these personalized models. The server could figure out how to combine the updates from different users in a way that respects those individual differences.
It's like we're all contributing to this massive AI brain, but our contributions are weighted based on our own unique experiences. That's powerful. What's another potential research direction?
Another cool idea is meta-federated learning. So FedMABench gives us all these different heterogeneity scenarios, right? Well, what if we used meta-learning to figure out which federated learning algorithm works best in each scenario? We could build a system that analyzes the performance of different algorithms across all these different data sets, and then automatically recommends the best one for a given task and data distribution.
So it's like FedMABench becomes the training ground for this meta learner, which then becomes a super smart algorithm picker for future research.
Exactly. It would save researchers a ton of time and effort. And it could also help us identify the limitations of current federated learning approaches and guide the development of new, more robust algorithms.
It's like we're using the knowledge gained from FedMABench to bootstrap the next generation of federated learning. It's a really elegant idea.
And just to be clear, these are just speculative ideas. We're not claiming to have all the answers here, but that's the beauty of research, right? It's about asking these questions, exploring these possibilities, and seeing where they lead.
Couldn't agree more. Well, it's been a fascinating deep dive into FedMABench. It's clear that this benchmark is a major contribution to the field of federated mobile agents, providing a standardized platform for evaluation and opening up a whole new world of research possibilities.
And it really highlights the importance of thinking about heterogeneity, of acknowledging that people use their devices in different ways, and designing our AI systems accordingly.
It's a reminder that the real world is messy, and that's okay. In fact, that messiness is what makes it so interesting. So to our listeners, what are your thoughts on this whole federated mobile agent thing? How do you think we can balance the power of collaborative learning with the need for privacy and personalization? Hit us up in the comments. We'd love to hear your ideas. And for those of you who want to dive deeper into the nitty-gritty of this research, we got a link to the paper in the show notes. Until next time, happy learning.